Hello everyone. In this video, we're going to demonstrate the validity of this argument. The conclusion along the bottom of this main scope line is for all x, if dx, then not rx. And it comes from two primary assumptions, both existential generalizations. The first one is there's an x for all y, dy, if and only if y equals x. And the second one is there is a z, dz, and not rz. What I would like for you to do is work alongside me with pencil and paper and make sure that you're hitting pause every once in a while. I won't stop to tell you when to pause and resume. So if I start to get ahead of you, feel free to hit pause, back up, correct course, work it out. Okay, so we're going to go ahead and get started. You can go ahead and hit pause now if you wanted to take a stab at this problem, or even just come up with a strategy for the initial steps. But if we look at the bottom, we have a universally quantified conditional, and a good standard strategy for proving these kinds of things is the rule universal introduction on an instance of that generalization. So I'm going to write down an instance here, dA horseshoe tilde RA. If we could put that together, then we can use universal introduction on it. The name A does not appear in any live assumptions, and in fact, no name appears in those assumptions. A conditional is usually proved by conditional introduction. There are often other ways of doing it, but in this case, conditional introduction is really necessary. There isn't another really good, that's a dangerous thing to say, but there isn't another really good way of proving it. So we'll start a subderivation on line 3 for conditional introduction. And the assumption for that subderivation will be dA, which is the antecedent of the conditional we want. That's an assumption for conditional introduction. And the last line of the subderivation is going to be the negation of RA, which is, of course, the consequent of the conditional we want. At this point, we have to look up at the two primary assumptions we have to work with. They are both existential generalizations. There is only one way to work with existentials, really, and that is existential elimination. And what that means is there are two existentials to work with. We've got to set up two subderivations for existential elimination. Let's take a look at what those are. Okay, we might as well take the two existential generalizations in order. So on line 4, we'll start our assumption for existential elimination on the existential on line 1. We'll introduce a name new to the proof, and it's to remain isolated to this subderivation. The instance on line 1 then would be this, for all y, dy, triple bar, y equals B. So we took the existentially quantified x out of line 1 and put a B in for it. That's an assumption, again, for existential elimination. And then on line 5, we'll start a subderivation with an instance of the existential on line 2. So dC ampersand tilde RC. That's an assumption, again, for existential elimination, this time on line 2. We also need to think about what our targets are going to be for these subderivations, and we're just going to use the target from the conditional proof. So tilde RA will be the target for both. We're going to get those sentences inside these subderivations, and we're going to, once we get to those sentences, we're going to just bump that sentence out to the outermost subderivation scope line for conditional introduction. Okay? And we also want to make sure, because we're doing two applications of existential elimination, we're planning them, let's go ahead and keep track of what exactly we're doing, because this is a potential for confusion. So this tilde RA is going to come into the proof from line 1 and the subderivation that starts on line 4, existential elimination. And then this tilde RA, this one, is going to come from the existential on line 2 together with the subderivation that starts on line 5 by appeal to existential elimination. I want to continue with goal assessment a bit. We don't necessarily have to. At any point, we could just start back up here with our assumptions. There's a lot of assumptions now, and start hammering out just rule applications and see where we go. But I think it's worth stopping and looking here at this tilde RA. How might we get it? And again, at this point, it's just, we can just make things up. We can just dream up some possibilities. So I'm looking at this tilde RC and thinking I can get that on a line by itself relatively easily. Tilde RC comes from line 5, ampersand elimination, right? That's just a pretty easy rule to apply. But if I can get tilde RC, then that will give me tilde RA if I could also get A equals C. So if I can get A equals C, I already know how to get tilde RC. That's going to give me my target, tilde RA. That's going to be by identity elimination. We'll have to come back and put the line numbers later because I have no idea what they are. But if I can put these two together, and this one's easy, if I can get my identity here, A equals C, that will let me get my target, tilde RA, and then boom, boom, move it out to the conditional proof, get my conditional, get my universal generalization. That would be great. So my plan is to get this identity statement, A equals C. So what we want to look at now really are our 3 auxiliary assumptions. And I want you to have your eye on this dA, and I want you to have your eye on this dC. Notice those two names, A and C, make up my identity statement here. And then I have a universal generalization. Interestingly, it's a universally quantified biconditional. On the left side is this one-place predicate D, which should be talking to this dC and this dA. And then on the right side is an identity statement, y equals b. So that's going to be very helpful information to keep in mind. If you want to, this would be a good time to hit pause and see if you can work out this identity. But I'm going to go ahead and make the first couple of moves. So the first thing I'm going to do on line 6 is break off DC from line 5, conjunction elimination. And then I'm going to go up to line 4, and I'm going to instantiate it on line 7, and I'm going to use the name C. So DC triple bar C equals B. That comes from line 4, universal elimination. And then on line 8, that gives me C equals B, doesn't it? C equals B, and that comes from 6 and 7, triple bar E. And it looks good. I've got an identity statement with a C in it, C equals B, and I'm after an identity statement with a C in it, A equals C. I count that as progress. If you followed along this far and things are going okay, I believe that you could probably hit pause and finish up the remainder, fill in this gap. And I encourage you to do so. So here on line 9, we're going to go back to the well, line 4, to universal generalization. It's an inexhaustible source of instances. We could just instantiate all day. So we're going to drop the quantifier and instantiate this time to the name A. dA, triple bar, A equals B. That's again from line 4, universal elimination. Line 3 up there says dA, doesn't it? 3A, dA. So together with line 9, that gives me A equals B. So that is 3 and 9, triple bar elimination. Line 11, we're there. We are there. That is from lines 8 and 10. 8, 10, identity elimination. Some of you may be bored by this, but I'm going to go ahead and do it. Line 11 comes from 8 and 10. 10 is the context for substitution. So we're taking A equals B. We're taking the B out and putting a C in. That's how we get line 11. Take the B out of line 10 and put a C in for it. We're justified in doing that because C equals B. That's what line 8 says. So line 11 comes from 8 and 10, where 8 is the identity that justifies the substitution, and 10 is the context for substitution. Then on line 12, we now know it is line 12. Tilde RC comes from line 5, conjunction elimination. Line 5, conjunction elimination down there on line 12. And then on line 13, this is where the plan really comes together. That comes from 11 and 12, identity elimination. And obviously line 12 is the context for substitution, and 11 is the identity justifying substitution. We just take the C out of line 12, put an A in for it. We're justified in doing so by line 11. Okay, so now it's just a matter of tidying up our annotation on lines 14, 15, 16, and 17. Okay, so line 14 comes from the existential in line 2 and the subderivation that runs from 5 to 13. That's an application of existential elimination. Line 15 comes from 1 and 4 through 14, existential elimination. Line 16 is our conditional proof. It takes the subderivation running from 3 to 15 as input. And then line 17 comes from universal introduction on line 16. It all worked out. All right? And there's our little proof.